All right, hello. So my name is Haven Skinner, and I'm going to talk about using Pyrope, a new hardware description language, to create transformable RISC-V architectures. So the challenge that we're hoping to address here is that, of course, hardware design is difficult, and there's some aspects of it that make it even more difficult than many traditional software projects. First off, it often requires multiple code bases. It's not uncommon to see a cycle-accurate version for synthesis in something like Verilog, a high-level simulation for design space exploration, and some kind of a verification reference model. Also, of course, hardware designs are organized into pipelines, and it's a known problem that adding and removing pipeline stages is also a difficult problem. And the added need, of course, verification becomes more important when you're doing a final tape out. And so we've created at UC Santa Cruz a new hardware description language called Pyrope, which directly addresses these issues. So the hammer that we use to help with this is fluid pipelines. These are a type of latency and sensitive systems. Prior work has shown that you can transform fluid pipelines adding and removing registers, which changes the timing aspects of the system without changing functionality. And as part of the Pyrope compiler, or any type of fluid pipeline system, you can apply these transformations as part of the compilation flow without having to touch the code base, pragmas, macros, et cetera. So I'll talk more about how that works. But first, a quick background on fluid pipelines. That they're a type of latency and sensitive system. And so we put elastic buffers, depicted here, between pipeline stages as opposed to traditional clock synchronous registers. So an elastic buffer, it has a data path, D, N, and Q. It also has a valid control signal, which indicates, of course, when data is valid, and a stop signal, which travels in the opposite direction to handle back pressure. So using elastic buffers, and a pipeline using these should be able to tolerate any sort of random delay. And we, in fact, recommend, as part of the verification, to actually have elastic buffers add random delays to test the rigidity of the system, because it's important in order to do pipeline transformations to conform to the fluid pipeline protocol. And so I'm going to quickly show with an animation what that looks like. So here we have valid data along a pipeline path. And then the next cycle, it travels. Now we have another piece of valid data coming. So they both are traveling down. And then we have a stop signal. And why the stop signal appears, it could be random. It could be some sort of a resource requirement. But it's important that the pipeline be able to still function properly. In this case, the other valid data should be able to pass. And then we have after the stop goes away, then the original valid, the first one to enter this path, should also pass. And when designing the fluid pipeline, it's important that the system be able to handle that sort of out-of-order behavior. And the reason for that is because if it does, you can safely apply pipeline transformations. Prior work defines a few different types of pipeline transformations. For this talk, we're very focused on collapsing. And so we depict that here. The F1 and F2 represent combinational logic, functional units, and the gray boxes represent elastic buffers. And doing a transformation, we're able to collapse the elastic buffer in between the two stages. So now we have one larger stage with the same behavior as the original two, but with different timing aspects. And so we found that just collapsing stages has a lot of uses at different parts of the different parts of the hardware development cycle. So if you collapse all the stages of a pipeline, going from however many it originally has down to one, you've kind of created a fast emulator. And our compiler, we can actually implement the system in C++, creating a fast emulator from the synthesizable code base. And in a second, we'll compare its performance against a RISC-V emulator written in native C. This also allows you to change the number of pipeline stages automatically in the design as part of the compilation flow. So we'll look at also in a second taking a 4 or 5 stage processor written in RISC-V processor written in fluid pipelines and turning it into a 2- and 3-stage one and compare those against 2- and 3-stage processors that were designed by hand with that number of stages. And then formal verification as well. Constructs such as forwarding paths are really designed to better optimize pipeline systems. And if you were to collapse them all into one stage, the forwarding paths should get optimized away. And so we'll look at using just a standard SAT solver from the YOSIS suite to verify designs that were different originally, different numbers of stages, and collapse them and then just use a hard SAT verification to confirm that they are identical. So first, looking at the simulation results. So we have our baseline, which was just compiling our fluid pipeline into Verilog, running it with Verilator. And on the system we used, we got about 2 MIPS using Verilator GCC. Now, collapsing the system into a single stage, we lose cycle accuracy, but we get to nearly 8 MIPS. And this is with no changes to the code, just collapse the whole pipeline and run it. And these were, of course, verified as well using a standard emulator to assure that there's no major bugs or anything. So now here's the performance that we got using Spike. Which, as many of you know, is the reference RISC-V emulator written in C. We keep Spike in warm-up mode to be consistent with our fluid emulator. And it's around twice as fast, a little under twice as fast. And so we also looked at the possibility of sampling. As many of you know, sampling is a technique of using a fast and a slow implementation, a fully cycle accurate one and a fast one, to speed up the simulation. And we found, this was using the SMARTS sampling schema, we found roughly the same ratios between using the fluid emulator for sampling versus using the traditional Spike emulator for sampling. Except, of course, the fluid sampling version, we're using the same code base, just compiled with different transformations. So synthesis as well. So we collected several RISC-V cores. The authors of many of them, I think, are in this room. And we compare these, against our fluid pipelines in terms of synthesis results. And we found, so C4 is a 4-stage fluid pipeline. Then we also looked at it with forwarding paths. We created a 5-stage fluid pipeline with forwarding paths. And so we see Pico RV32 is also 4-stage. This delay only looks at delay in terms of time. This doesn't look at CPI. Our CPI is a little bit higher than Pico compared to the delay. V-scale is 3-stage. Zero RISC-V is 2-stage. And so you can see it's a little slower in the delay, better in area. These cores, of course, were just made by me personally as well, using Pyrope. And then we looked at some transform variations of our fluid cores. So we take our C4, we transform it into a 2-stage, and then we see it gets pretty close to zero RISC-V. The 3- and 4-stage, or the 3-stage variants didn't, not quite as well. But we were excited to get kind of the range of values we were looking for and a lot of consistency when we do these kinds of transformations. Finally, on verification, so as I said, we can collapse cores and then structures like forwarding get optimized away. And we ran 4, 5, and 6 core variant, 4, 5, and 6 core fluid pipelines made by hand in those number of stages. We just collapsed them all, verified them all against each other. Every single time it passed. Using the YOSIS suite, the verification didn't take longer than 2 minutes, so it didn't become an extremely large or open-ended problem. And we were really excited to see kind of the consistency that we were looking for in that. So in conclusion about Pyrope, it's a new hardware description language which we've designed specifically for creating fluid pipelines. I created the 1.0 compiler myself by hand, in collaboration with the whole lab with regards to the language. Another one of our students, Akash Swindhar, is building the 2.0 parser. We've got a little tutorial up, and we're looking forward to releasing the full compiler, along with some other kind of planned features, fast code generation, and hot reloads. And so my advisor wanted to point out his license plate. You can see this in the hotel parking lot where the shuttle was. He actually made Pyrope his license plate. So we're very excited about this project, and we're committed to expanding it in the future. There's actually no questions here, but feel free to email me or talk to anyone in our lab about this project. Thank you.